Hello, my name is Jeff Kindart, and today we're going to talk about irrigation. There are many different forms of irrigation. Overhead irrigation was commonly practiced up until the 80s throughout pretty much the entire United States. And here are a couple of examples of different types of overhead irrigation systems. On the upper left is a system that consists of movable pipes. These typically pipes are 20 foot in length, and they can be disassembled and put onto a wagon, moved to a new field, and reassembled. In the bottom right hand picture is a picture of a linear system. It's most commonly used on sod farms, but you can see it for some lower stature vegetable crop production. And in this case, it's a little bit like a center pivot, only the wheels are much smaller and it just rolls across the field and waters in a straight line, hence the name linear. Other types of overhead irrigation systems that can be employed. This is an example, a couple of pictures of something called a traveling gun. And as you can see here, traveling guns just ride down the hose that has been laid out. They roll themselves back up, and they are very useful for crops that are durable. We'll see them used sometimes for sweet corn irrigation, but they're probably not the best choice for crops like tomatoes that could be damaged by the very large stream of water that is placed upon them as the gun moves around. So very good systems for turf, good for durable vegetable crop production, not suitable for all types of vegetable production. This is a center pivot over the top of some sweet corn, and center pivots, or in some of these systems, may actually operate linearly also. This is a system that we've got enough clearance, they're very high framed, and they can get over the top of any crop that you're going to be raising in the field in which they are irrigating. Those types of systems still exist, and for example, the movable pipe and overhead irrigation is still a mainstay for strawberry growers who are wanting to practice sprinkler irrigation for frost protection. But by and large, most of the specialty crops in Illinois are now watered using what is referred to as either micro or drip irrigation. And the reason for this transition is a couple of fold. One, the initial expense is probably not as much, although the expense over a period of time is likely greater. But when you go to buy a lot of aluminum pipe to irrigate your farm, it's gotten to the point where it's quite expensive. And, you know, if we depreciate the expenses out across the 10 or 15 years that the system may last, it's not too bad on a per year basis, but the initial expenditure is quite high for many of the overhead systems that we looked at when we contrast it to what the initial investment is to irrigate an acre using micro or drip irrigation like you see here. So in addition to the relatively lower expense associated with this, drip irrigation is also able to operate at much lower application rates on a per minute or per hour basis, and that affords us the ability to utilize smaller water sources and smaller pumps and pipes and things that we're going to need in our irrigation system. Because the flow rate is relatively low on a per minute or per hour basis, that allows us reduction in the size of required equipment. Additionally, one of the things that you'll typically see touted as an advantage of trickle irrigation is that it is much more efficient. And that is accurate, but I do want you to realize that this efficiency is based on efficiency per unit of product produced, not efficiency based on the amount of water you're going to use on a per acre basis. For example, if I were to compare and contrast overhead watering an acre of peppers with an overhead system versus a trickle system, at the end of the year I will have put more gallons of water on the trickle irrigated acre than I will have put on the overhead irrigated acre. However, it is likely that I will pick somewhere around 2,000 bushel to the acre on the drip irrigated field, as opposed to probably only 1,000 to 1,100 bushel per acre on the overhead irrigated field. So it is more efficient, but the efficiency is in per unit of product produced. It's not exactly a reflection of a reduction in the amount of water we're going to use on a per. This is just sort of a diagram of a typical drip or trickle system that might be utilized, and it starts in the upper left where we've got a pump source and a pump and a water source, and as we come out of that, we're going to have the ability to inject fertilizers. Those are the big tanks that you see in the background, and other chemicals that may be required, such as chelating agents. The system then goes on and goes through a set of filters, and it then is distributed out through what is termed manifolds or headers out into the crop area itself, and then down each individual row of crop you're going to have either sprinklers, small micro sprinklers, or T-tape run for distribution of the water at the end source. And we talk about emitters. Emitters simply refers to the hole that is in the distribution tubing that lets the water out. And one of the advantages of these over something like a soaker hose that you're likely familiar with, in these systems the holes are laser cut or machined in such a fashion that accuracy per foot is very high, and they have a great degree of uniformity. If we take a typical soaker hose that we buy from a box store and we stretch 100 foot of it out or 50 foot of it out across the floor, hook it up to the water, turn it on, and we set 3 cake pans underneath of it at 3 different places, we'll find that one of the cake pans is going to be filled with water and overflowing, while the another one is going to be maybe half full, and a third one may have very little water in it whatsoever. There's not a great deal of consistency in foot-to-foot distribution on soaker hoses. With these types of commercial systems that we're talking about, we're going to have wonderful uniformity. Every hole is going to let out the exact same amount of water, assuming we've done everything correctly. There are basically 2 types of ways that this micro irrigation can work. One is that we can have a solid piece of tubing that we actually punch a hole in for our emitter, and when we do that, that's referred to as a point source emitter. And so we can use point source emitters for things like orchards or some of the bush fruit that we might be growing, things like blueberries. What's more typical is the use of line source emitters, and these would be things like trickle tape, where the actual emitter is made as part of the manufacturing process, and you can get them spaced at different spacings depending on what you order. 12-inch spacing is pretty common for vegetable production in the state. And here are some examples of one of the products that could be bought and used. This would be typical on plantings like blueberries or grapes. This is a Netafin product, and you can see that you can order it with spacings of 18-inch, 24-inch, 30, 36, 42, 48, 60. You can get whatever spacing that you need to match up with how your plants are arranged in your field. Again, this would commonly be used in orchards, Christmas tree plantings, and perhaps even in something like blueberries and grapes. Here's a different way that you might go about irrigating, and in this case we're going to lay solid pipe down, but we're going to put micro sprinklers as point source emitters punched in exactly where our tree is located at. And in the right hand column you're looking at 3 different types of micro. And so you can see this picture sort of shows everything that's involved with that. In the bottom left is the large black tubing that's going to run down the entire length of the row. In the upper left is the emitter. It's barbed. It gets punched into the large black tubing right below it. On the other end of that barb goes the tubing that is on the bottom right, which is typically referred to as micro tubing. and that microtubing is going to turn around and feed the actual sprinkler, which is in the upper right hand picture. This is a slide showing a more typical utilization of drip irrigation rather than point source irrigation like in the previous slide. In this case, we're using trickle tape and distributing the water down each individual row of tomatoes. This is probably the most commonplace and the most typical utilization for beginning growers is the use of tape like you see here. The utilization of trickle tape is relatively intuitive. You simply need to get the tape close to the vicinity of the plant's root zone, and we have it hooked up to some type of a header. In this particular case, it's lay flat. There are a variety of materials that can be utilized, and that's going back to a water source of some type. Although the systems are intuitive, we do see growers run into a variety of problems when they first start utilizing irrigation, and we're going to address the rest of this talk by kind of talking to what are some of the problems that we commonly see, and hopefully by discussing that we will allow you to avoid having any of the kinds of problems that are commonplace throughout the Midwest. The first problem is water source problems, and water source problems, in other words, where our water coming from, what type of problems we would anticipate depends on where we're getting our water. If we're getting water from a surface source, an example of such a thing would be like a pond or a lake, we can have problems with surface sources being contaminated with herbicide. We can have problems with the surface water source containing disease organisms, which we pick up out of the pond and then irrigate throughout our field. We can have problems with the size of the surface source, and we can have problems with excessive algae. If we're using a well for our source, then we have to look at things like the size of the well and its capacity, and we also have problems in Illinois with iron and sand. And if we're on a city or municipal water system, then the most common problems that are going to be encountered by growers are going to be problems related to the issues of volume and pressure. Here are some examples of the surface water problems. If you look in the upper left, the particular watershed for the pond that was used for watering the strawberry field was surrounded by cornfields. The cornfields had been treated with atrazine, which washed into the pond. When the grower picked up the irrigation water out of the pond and distributed it out through his strawberry field, he also moved the atrazine that had washed into that pond with it, and you're seeing atrazine damage on strawberries that is a result of a contaminated pond. In the upper right, you are seeing strawberries with black root rot, and black root rot can be caused by Fusarium, Rhizoctonia, Pythium, and Phytophthora. All four of these organisms can be washed out of a field and into a water supply, picked up in the water supply, and pumped out similarly to the atrazine in the previous example. One of the best defenses against this is maintaining a good sod buffer strip between any cropland and the pond that you're going to be using for irrigation. The bottom picture is showing what was a common sight a couple of years ago when we had a drought through Illinois, and that is growers that had ponds that were of sufficient capacity for normal years, but in a drought year they actually irrigated to the point where they pumped their ponds dry and no longer had any additional water available for irrigation. So we do want to make sure that we've got a properly sized pond if that's going to be our water source for irrigating throughout the entire season. We've got to make sure there's enough capacity in that pond to meet our needs for the algae can be another problem associated with lakes and ponds, and in some cases it can be a very significant problem. And algae problems can do a couple of different things. Filamentous algae can actually clog intake pumps and screens and filters. Additionally, blue-green algae, which isn't exactly algae but will work for the purposes of this conversation, blue-green algae can be picked up out of the pond, and it actually is no problem to go through all of our filtration in terms of screen filters, but it will continue to grow inside of our black tubing. it gets to be a larger size colony. The next time we turn on the water, it plugs up all of our trickle tape emitters, and we wind up having clogged emitters. How do we get around algae problems? Well, one of the first things we do to avoid clogging our intake screen, which you see in the upper right, is that we're going to want to keep that intake screen suspended above the bottom of the pond. And we can do that by simply making a floating raft like you see in the upper right hand picture, and then suspending the intake foot filter from the raft with a rope, and we keep the rope short enough that we are not contacting the bottom of the pond with it, where most of the algae is going to be present. To address the blue-green algae issues that exist, about the only decent way to do that is by the utilization of sand media filters. And for small operations where we're irrigating perhaps less than 3 or 4 acres, common swimming pool filters would typically be used. If we get to larger size operations, then in the very bottommost picture you can see larger stainless steel sand media filters can be employed, but in all honesty, they just have a greater capacity. They operate in the exact same way that the swimming pool filter operates. One of the things you will notice in both examples of the sand media filters, the pictures that are shown, we always have to have 2 filters. The reason for that, if you guys have had a swimming pool, you know that periodically you have to back flush these filters. Well, if our source of water is a pond, in order for us to back flush a filter, we need to back flush it with clean water. The only way we can do that is by having 2 filters, so that we can utilize one filter to back flush the other filter. We've got to have 2 of them. One of them is going to be required for back flushing so that we can obtain clean water to backwash the second filter. So that's sort of the surface water problems. Again, in review: herbicide and disease contamination, the size of the physical impoundment, the structure itself, is going to have sufficient capacity to meet our needs for the entire summer, and we need to work on controlling excessive algae that may be present on surface water sources. And it's just almost incumbent that you utilize a sand media filter when using surface water. Next, we're going to talk about wells, and in this case we're going to worry about size and capacity, iron content, and in some areas sand as well. Iron content can be a real problem, and the situation is one that is hard for growers to know immediately if they have not taken a water sample and had it submitted to a lab and had that sample of irrigation water evaluated for suitability for use as an irrigation supply. The problem with iron is this: iron comes up from the well where it has not been exposed to oxygen. It comes up in the reduced state. As it contacts oxygen in the process of getting pumped out and distributed into the field, it winds up, iron hydroxide becomes oxidized, and it results in an orange slime or almost an orange jelly. And you can see this orange on the pipes in the picture that you're seeing here. And if it's only a small problem with iron, we can just simply inject chelating agents that will keep that iron in a form that does not oxidize, and we will not have trouble with it blocking our emitters in our T-tape. If we have a high iron content, as was the case in this field right here, what's going to happen is, in this picture you're seeing, here's an example of one that's being run. We're actually going to bring the water from the well into this crawdad aerator to begin with, and try to immediately oxidize as much of the iron as is possible and get it to precipitate out prior to picking it back up and distributing it through the field. Again, in this case, we're going to utilize the sand filters that you see here. Some wells in Illinois also have a problem in bringing up sand with the water that they're pumping out of the well. That can be easily addressed with cyclonic filters like you see here. These are three different examples of filters that are designed to remove sand that has been pumped with the water out of the well. They work quite simply by when the water enters, it has to flow in a circular pattern. The centrifugal force results in slinging the sand to the outside, and it simply drops down to the very bottom. And you can see in all examples we've got a valve we can open to drain the sand out and reclose the valve. And the nice thing about these filters is that they're relatively easy to maintain. If you do not have a sand media filter downstream from a pump and a well that is bringing up sand, it is imperative that you have one of these cyclonic filters for sand removal. So we've now addressed sort of the common surface and well water problems. Now let's talk about some of the municipal. If you're going to use a city water or municipal water system, what some of the typical problems are that you're going to. The first thing you need to know is that if you're using a municipal water system for irrigation, it is imperative that you have a backflow preventer, sometimes commonly referred to as an RPZ, which simply stands for Reduced Pressure Zone Backflow Preventer. The reason that we have to have this, if we're injecting fertilizers, as you see in the bottom left-hand picture, there's a break out in the municipal water system. What will happen is we can back siphon the pesticide or the fertilizer into the municipal water system if we don't have a backflow preventer. If that happens, the grower in the state of Illinois is liable for replacing however many meters have to be replaced and decontaminating the system. So there is a very expensive fine associated with getting caught and not doing this. Worse than that, there is the potential for having to pay back to the water district a tremendous sum of money if they have to go in and replace your neighbor's meters. And even worse than that, there is the potential of hurting someone if you don't have one of these reduced pressure zone backflow preventers in place. So if we're going to do this, let's do it right. I don't have any problem with using municipal water for irrigation, but we do need to get our backflow preventer in place, installed, inspected, so that we're in. The next problem with a municipal water system is that most of the time a typical household will only have a 3/4 inch meter, and if you'll look, the maximum output that's capable of, I mean absolute maximum, is 30 gallon, and we would rather have something that can supply more water than that, so we have to go to a larger meter, either an inch or an inch and a half. Most growers don't go to 2-inch, but when we go from a 3/4 to an inch, you can see we almost double the amount of water that's available for us to irrigate with. If you have a 3/4 inch meter and have to replace it with a 1-inch meter, you'll have to contact your water district, and they typically are going to do the installation of the meter, but you're going to have to write the check for the meter and that installation process. Now, there's some water source problems that we've talked about. Now let's talk about some of the design. I think the biggest design problem that we see is growers using too small of either a meter, like we just previously talked about for a municipal system, or too small of pipes to deliver the water. If you'll look, these are different flow rates. If we try to use a 1/2-inch garden hose, for example, the flow rate would be 6.8. If we go to a 3/4 inch garden hose, we again are doubling the amount of flow. When we go from the 1/2-inch to the 3/4, we've gone from 6.8 gallons per minute to 13.6 gallon per minute. We've got to have big enough pipe to carry the amount of volume of water that we're going to be needing to irrigate the area we are trying to irrigate. Why is it that basically when you double the size of the pipe, you increase its flow rate by 4. Why is that? Well, there's a whole bunch of engineering problems that illustrate this, but long story short, there are 2 types of flow that exist. Laminar means straight, and turbulent is like the eddies on a wing dam at a river where we've got the water flowing around. There's always turbulent flow associated with the side walls of the pipe because of imperfections that exist. As we increase pipe size, the percent of laminar flow increases relative to the percent of turbulent flow. So we've got less pressure being pushed back on and less resistance to the water flowing through the pipe. And so the flow rate increases again at a factor of every time we double pipe size, it will actually carry 4 times the volume of water. A typical example, if we're going to try to fill an Olympic-sized swimming pool with a garden hose, you're going to be there roughly about a lifetime to get that done, and we're going to have a pipe sufficient, like you see in the bottom left, capable of carrying enough water. Other design issues that we have. If you look at T-tape like you see right here, you'll look at it, there's actually a code printed on the tape, and you can go to the manufacturer of the specific tape that you're using and look up what that code means. But basically it tells you the diameter, which tends to be relatively fixed, but it does tell you the thickness. These come in different mils of thickness. 8 mil, 10 mil are pretty common. For perennial plantings like blueberries, we might use 15 mil. The thicker the tubing, of course, the more expensive that it is. The second number in the code typically tells you what the spacing is. How far is it in inches from hole to hole? The third number is telling you what is the flow rate. And most of the tapes will come in just 2 variations, either high flow or low flow. But the amount of flow that's occurring in a per minute per 100 foot figure is going to vary depending on what the spacing of the individual emitters are. Here's a diagram that shows you the wetting pattern of different soil types. If we have a very fine textured soil, something that's got a lot of silt or clay in it, we find out that the water spreads pretty widely and doesn't go down or penetrate near as deep. On sandy soil, we find that the water flows down very well, but it doesn't spread very far. So on soils that are very fine in texture, we can operate with a wider emitter spacing. On soils with textures that are very coarse, on sandy soils or soils with sand and gravel, then we need to have emitters that are spaced much closer so that when we get done watering, we have wet the entire bed face or bed surface where the plants are growing. Again, there are a wide range of spacings that can be purchased for things like T-tape, and as we change the spacing, that results in subsequent changing of the flow rates. The amount of flow out of each individual hole stays pretty constant, whether it's low flow or high flow, but how many of those holes there are in a 100-foot area winds up changing what our flow rate becomes. Obviously, the closer the spacing, then the higher the flow rate per 100 foot. Another thing about using micro irrigation or trickle irrigation, these systems are designed to be operated at low pressure when we get it out to the field itself. Typically nothing more than 15 psi. Common operating pressures might be somewhere in the 8 psi range. If we get much above 15 psi, we'll actually blow the lines up, and so we have got to have some way of controlling that pressure. On small systems, you simply use a small pressure reducer like you see in the upper left-hand corner, and the systems, as they get more complex, have different mechanisms for doing this, but in all trickle systems, we need to have some mechanism of regulating the operating pressure, again, so that we're staying in that 8 to 10 psi range, not getting above 15. Here's an example of what happens when you get above 15. You can see that the hose has literally blown apart. Okay, we've talked a little bit about water source problems and design problems. Maintenance. One of the things we'll find if we didn't do a good job getting our water filtered, or if we didn't address iron issues, we may wind up clogging emitters. If that happens, very honestly, it's not a good situation. Some growers will run hydrogen peroxide, something like oxidate, through the system, which does have a label for it, and in some cases that may help clear some of the clogged emitters. But our two best defenses to avoiding clogged emitters: one, have good water filtration on the system. Secondly, when we lay tape, it is laid so that the emitters are facing up rather than facing down. That way, when you shut the system off, it doesn't all drain out the lowest spot in the field. What things can cause clogging emitters? We can have physical problems such as silt or sand, again, easily taken care of with filtration. We can have biological problems such as bacteria or blue-green algae causing us problems. Most of those can be addressed, again, through sand media filtration. The third mechanism for clogging emitters would be chemical, where we have problems with, again, in Illinois, typically is going to be iron. Or we may have a problem with the fertilizers that we have injected, resulting in some sort of a insoluble precipitate being formed, and that can result in clogging of our emitters also. We talk about iron quality. Here's a little chart that shows you if we go and have our water tested at a lab like Spectrum Analytical or A&L, when we get our test results back, what is our pH and iron content, manganese content, some of the things that we look for, and this is showing you whether or not it is not very likely or very likely that you're going to have a problem based on what your water test results are. The biggest problem by far with irrigation is lack of the growers to do a good job in managing the system. There's lots of different methods we can use for monitoring soil moisture levels. The feel method, where we kind of reach down by the plant where we're irrigating and grab a chunk and see does it feel wet, is probably a very common method that's used. Additionally, there are things like neutron probes, electrical resistance, soil tension. May even use plant indicators or computerized irrigation scheduling, but we use something other than driving by the field at 55 miles an hour, looking out the window and going, nope, plants are still green, they don't need. Again, here's an example of a neutron probe. They work well. They're really only for the top 1% of growers. They're very expensive. They work great, but not overly applicable for people getting started. This is a device on the right-hand side that measures electrical resistance, and those are typically going to be referred to as something like a Boykus block, and those also can be utilized probably more commonly. There are different charts that tell you what the recommended length of tensiometer it is, depended on what the crop is that we're trying to raise. Yeah, if we rely on just an app to do things, we may wind up with a slight over-application of moisture. Anyway, to reach us, you can call or email, and we will do our best to answer any questions that you